All right, now we're recording, and hopefully there'll be some time left for any homework questions. Officially in Canvas it says first assignment is due 11:59 p.m. tonight. But generally I don't actually look at the homework until like that weekend. So that's my tradition. I ruin Saturday by grading homework. Yeah. And but at least there aren't very many of you, so that helps. So I much rather have something that is turned in late more complete than something that's turned in by 11:59 and having left blank. Even if that does make my grading easier. I do try to give a fair amount of partial credit. So you can help yourself by putting down what you can. You can work it all the way through. Okay, so today in the next section about linear operators, such in particular differential operators. So if you think of f prime of x, you normally think of that as a function, especially when you have a concrete function given. But you can also think of it as the differentiation operator applied to function f of x, and the result is f prime of x. So here we're going to learn about certain properties that linear operators can have and how to work with them. So an operator, as opposed to a function of transformation, what makes something an operator is when it's applied to a certain domain, and the result is from that same set. So the domain and range of a function are the same, then it's appropriate to refer to that function as an operator on that domain. So what we will be looking at are operators that act on Hilbert spaces. So we'll define an operator that acts on a function from a Hilbert space, and the result of that operator is a number function in that Hilbert space. The way we write it is like if H is our Hilbert space, and A is an operator, so we will typically use uppercase letters to refer to operators. Lowercase letters refer to functions, as they usually do. Then G equals AF means the operator A is applied to a function F, producing the function G. The kind of operators we will be studying are the nicest kind, linear operators, such as differentiation. So what makes an operator linear? It's these properties right here. So A and B are linear operators, F and G are functions from a Hilbert space. Then applying a sum of linear operators means you get to a function. This means you can apply the operators to a function individually and add the result together. So we have a distributive property there. We also have a distributive property for functions. A applied to a sum of functions is the same as applying A to each function individually and adding the results. And finally, an operator A applied to a constant type of function. You can pull the constant out. So you can apply the operator to a function first, and then multiply this scale by the scalar. Maybe remember from a linear algebra class, the notion of a linear transformation. A linear transformation is a function that has some domain, some vector space as its domain, and a different vector space as its range. And a linear transformation would satisfy these properties also. And when a linear transformation has the same vector space as both its domain and range, then it's a linear operator on that vector space. So that's exactly what I'm talking about here. All right, right, as I mentioned, differential operators are the operators we will be most interested in. And so what constitutes a differential operator? You are either taking derivatives of a function, or you may be multiplying function by another function, which is called a coefficient in this context. And so then your linear differential operator would involve several terms of that form. Here's an example right here. So here I'm using a fancy L, or calligraphic L, to refer to a differential operator. And what does the differential operator do? It's acting on the function y, that's the input. So to get the output, I take the second derivative of y, then multiply that by x squared, plus y prime times x, and then plus this function times y. What makes this a linear differential operator is that the coefficients involved, the x squared here, the x here, x over here, they're functions of x. They are not allowed to be functions of y. They can't, so they can't depend on y at all. The only thing we're doing to y is either differentiating it or multiplying it by a function of x. Also, you can't do something like dy dx, the whole thing squared. That would not be a linear differential operator, that would be nonlinear. I can't do something like derivative of y squared, that would also be nonlinear. So all you're doing is you're taking derivatives of just plain old y and then multiplied by functions. And then adding them up. That's all that's allowed. Linear differential operators can either be constant coefficient or variable coefficient. This particular one is variable coefficient because the coefficients do depend on x. You would see a lot of, in Math 285, you mainly saw differential equations that had constant coefficients, especially in anything you did like second order on up. Most equations you dealt with would have constant coefficients. So this differential operator, this particular one, is used to describe what's called Benzel's differential equation, or Benzel's equation, which we'll see some more of later, and later on we'll talk about Benzel functions. So this operator is actually the left side of Benzel's equation. So if you define differential operator L to be this, then you can write Benzel's equation as Ly equals 0. So naming differential operators, defining differential operators in this way makes it possible to write differential equations in a very concise way, and that helps facilitate the analysis of them. Okay. Now, linear operators on a vector space generally do not commute. So you cannot expect to do this. Like the way this is written, I have a function f, I'm applying the linear operator b to it, and then I apply a to the result. Whereas over here, I apply af and then b. So you should not assume that those are equal. Now, if you have two operators a and b from which this does hold, for any function f, then it does happen from time to time. Then we say that a and b commute. And this leads me to an expression that is called a commutator. So the commutator a and b is defined using this notation. So square bracket a comma b. And that's just defined to be AB minus BA. So if a commutator of A and B is 0, that means AB equals BA. So then it's in that case that the operator is A and B. And for mathematical physics, the commutator is a good expression to be familiar with. Actually, this the expression involving a commutator happened to pop up in my research once, and it turned out to be very handy, because then I could look up certain results that are known about commutators and like simplify my expression even more. Here's an example involving a commutator. So here's my operator A. It's just a differentiation operator, so AY is dy dx. And then the operator B is defined by multiplication by x. So dy is xy. So I can figure out what the commutator of A and B is. So here I get this just by the definition. So in this case, the first term, B is applied first. So I have xy. And I take the result of applying B and I apply A to that. So differentiation of xy. Whereas with BA, A is applied first. I take the derivative. Then B is applied. I multiply that by x. So we see the difference in the two. That's multiply, then differentiate, differentiate, then multiply. So now what I do is I expand this using a product rule. So product rule, derivative of xy turns out to be this. So y times x prime, which is 1, plus x times y prime. But then we have a cancellation, and the whole expression turns out to be y. So what's interesting is the commutator of A and B, which is itself another operator, ends up being equivalent to what's called the identity operator, which we'll talk about more later. So because even though A and B both change y, commutator of them does not. So and these are different operators. The A and B do not commute, because if they did commute, we would actually have a 0 right here. But it turns out that the commutator is similar to either operator individually in this case, anyway. Are there any questions up to this point?
So in this example, did it prove that it doesn't change it? It doesn't change it like every time?
It proves that the commutator of these two operators doesn't change the input.
Okay.
If I throw in different operators A and B, who knows what I would get? So this is just a strange example. Okay, here's some properties of commutators. The order of the arguments is important. So if I have commutator A and B, but I flip A and B, that changes the sign. And you can see that from the definition, because the commutator is AB minus BA. Switch A and B, then you get the same sign. We have a linearity, because we have a distributive property of either argument of a commutator. Also, if I have a constant of the commutator, I can move that inside and apply it to one of the operators, but only one, not both. Doesn't matter which one. So be careful about it. So here's another example involving commutators. So same operators as the previous example. So A is differentiation, B is multiplication by x. So if I apply b twice, that I can write that as b squared. So you're applying b twice, you're multiplying by x, and you're multiplying it by x again, so you get x squared y. So now if I want to figure out the commutator a and b squared, I can actually do that without even necessarily getting into what a and b are specifically, just using the properties of commutators that I did above. With a little trickery to this. So here I have, by the definition, commutator a and b squared would be a b squared minus b squared a. And now I throw this in, I'm subtracting and adding BAB. And I'm doing that because here I have AB as a factor on the left. Here I have AB as a factor on the right. But here I have AB times B. This is B times AB. They're multiplied in reverse order. So, or another way of putting it is, if I factor B out to the right, what's left is AB minus BA. So I apologize, I went down a useless track there for a second. What I really need to do is keep in mind here, you factor out B to the right, I have AB. Here I have B I can factor out to the left. And what's left? I have AB minus BA. Like I'll put in an intermediate step there, just to make it a little easier to see. So I have AB minus BA times B plus B times B minus. Okay. So I recognize these as commutators, and so I write it like that. Now here's where I fall back on what was worked out in the previous example. The commutator A and B turned out to be the identity operator. So commutator A and B times B turns out to be just B. And the same thing over here. So in the end, I get just 2B. That's what the whole thing simplifies to. So I can say that the commutator A and B squared applied to Y is the operator to xy. That's because B is multiplication by x. So I'll put that in parentheses to make it a little clearer. Yes.
How'd you get the minus BAB and plus BAB in the second line?
Oh, yeah, this is why I refer to it as trickery. That's because they cancel, like it's throw that in there. The goal, I guess, what you're also asking, a reason for throwing it in there is because I have AB as an initial factor. So AB times B. If I think of AB as a unit, so then I have to subtract from it B times AB. So the B is on the opposite side. That sets me up to get a commutator. But because I'm throwing this in here, then I have to add this. But then I can recognize this as an expression involving a commutator also.
So the third to last line.
This one?
Yeah, that one.
Yeah.
Is it just saying that these two are equal to one another and that they are equal to B? So they combine to be 2B.
Okay. So from here to here, is that what you're asking?
Well, just that
Or
line,
the next step.
the next step. That
Yeah.
line.
From here to here is because of what happened up here.
Oh,
That A commutator B turned out to be just the identity operator.
oh.
Yeah, because this is something that definitely would not be true in general.
Yeah.
Yeah.
Makes sense.
You have a question? So from that first example, that A, B, Y being equal to Y for all Y, the way we can abbreviate that is that A, B is called the identity operator. So the identity operator is the operator such that if you, whatever input you apply it to, the result is just that same input. So this is analogous to, well, the identity matrix from linear algebra is because it's kind of analogous to this. Your vector space is not a function space, but rather, Rn. The identity matrix is the identity operator on that vector space. So this plays the same role. So that leads to the concept of an inverse. So if so given some operator A in the Hilbert space, if there exists an operator B such that this holds, so A applied to B or B applied to A turns out to be the identity operator, then we say that B is the inverse of A. Now just as not every matrix has an inverse, not every linear operator has an inverse. So if it is, we say it's invertible. Another term for this is we also say that the operator is, not that. Non-singular. So if an operator does not have an inverse, we say it's singular. One property of operator that invertible or not invertible depends on when they produce zero. So if you have an operator A, and A applied to any non-zero function gives you zero, then it's not possible for A to have an inverse. So in that situation, A is singular, in the case where it doesn't have an inverse. When this happens. And we can see why it's not possible to have an inverse, because if I have AY equals 0, and multiply both sides, I apply A inverse, I assume that an inverse exists, and I apply it to both sides. So on the left side, I would have A inverse times A times Y, which is Y. But on the right side, I have A times 0 is 0. So I get a contradiction. I end up with the equation Y equals 0. But that's a contradiction because I'm assuming from the get-go that Y is non-zero. That's why, so if AY equals 0 for any non-zero Y, A cannot have an inverse. Now, while not every operator has an inverse, every operator does have what's called an adjoint. The notation for adjoint in our textbook uses the dagger, no adjoint. Other books use a star. Well, our books use the RDC star for complex conjugate. So what is an adjoint? It's defined in terms of scalar product. So suppose I have a scalar product of functions f with a g. So g is a function in a Hilbert space. We apply the operator a to it, and we get another function from that that's noted ag. So Here, A is applied only to G, and then we take a scalar product with F. But if you could write the scalar product in this form, where it's, instead of having an operator applied to G, it's an operator applied to F, and then take a scalar product with G. In other words, think of it as putting the shoe on the other foot. A is the shoe. So you're moving the operator from G over to F, but it's not necessarily the same operator. It's the adjoint. So the adjoint is the unique operator such that this holds. So F scalar product AG is the same as A adjoint applied to F scalar product of G. So moving the operator A across the vertical bar changes it to its adjoint. And every operator has one. I'll see examples soon where you can find out what the adjoint is and using this definition. But first, some properties. The adjoint of the adjoint is the original. So adjointing twice brings back where you started. Also, the adjoint of a composition, or if you want to think of the product of operators, is equal to the adjoint of the two operators individually, but applied in reverse order. You can think of the adjoint of an operator as analogous to the transpose of a matrix. We have the same kind of properties. The transpose of a transpose of a matrix is a matrix itself. The transpose of a product equals the product of the transposes in reverse order. The transpose of a matrix is the adjoint, is the same as the adjoint. So when you have this definition, instead of scalar products involving functions in Hilbert space, but rather dot products of vectors in Rn, the transpose of a matrix satisfies exactly this. So it's all the same concept. And the interchange of linear operators on the Hilbert space or whatever vector space, there's always a link to some concept in, like from introductory linear algebra class, the ordinary vectors in Rn. And it's helpful to keep those parallels in mind because it helps you understand concepts in number settings. And here I'm going to show the first property. So here I have F, scalar product of A adjoint G. Now, I can rewrite this as taking the adjoint of this operator and applying it to F. So that would be adjoint of A adjoint. But what I can also do, if I start with the same scalar product, I can reverse the operands by taking the complex conjugate. But then, by the definition of adjoint, I can move this operator over to F. And then it becomes A. But then, I'm taking the complex conjugate, so I can switch the operands and get rid of a conjugate. And that brings me here. Now I started with the same scalar product in both cases. Therefore, this and this must be equal. So sure enough, A is equal to the adjoint of its adjoint. Any questions about how this worked out? Illustration of properties of adjoints and also scalar products.
Okay. So about the adjoint and the inverse, I'm wondering if there are situations where an operator can have both an adjoint and an inverse.
Okay. So in other words, like when the adjoint is the inverse, is that what you're asking?
Yeah, whether an operation can have both an adjoint and an inverse.
Okay. I'm not sure if I'm if I'm correctly understanding you, but okay, did you say when the operator has both an adjoint and an inverse?
Yes.
Okay, well, yeah, because certainly it's very complex because every operator has an adjoint. Not every operator has an inverse, but operators certainly have both. And in certain cases, the adjoint and the inverse can be the same thing. And that's something I'm actually going to talk about a little later. I'm not sure if we're getting to the heart of your question, though. Like, I don't know if I addressed your question.
Yep.
Sure. Okay, so just making sure, and you're welcome to rephrase if you need to, but well, okay. And this may relate to what you're thinking about. So here's some terminology regarding adjoints. So if A is equal to its adjoint, we say that it is self-adjoint. The similar concept for matrices is Hermitian, so sometimes it's used to refer to operators. So that means the same thing if A is equal to its own adjoint. This is similar to the concept of a symmetric matrix, so an A is equal to its own transpose. Real matrix. Similarly, we have A being anti-Hermitian. It can also be referred to as anti-self-adjoint. If A adjoint is equal to minus A. That's similar to the concept of a skew symmetric matrix. If A is equal to minus A transpose, we say it's skew symmetric. And finally, if A has an inverse and its inverse is equal to its adjoint, it would say that A is unitary. If A is a real valued operator, we also say that it's orthogonal. And when this happens, what I can do is I can, if I using the sequence multiplying and apply A on both sides, that A adjoint A, which is the same as A adjoint, is equal to identity. This is similar to what you get from an orthogonal matrix. The matrix A is orthogonal. A transpose times A is identity. Now, here's an example of finding an adjoint. The Hilbert space we'll consider are all functions that are twice continuously differentiable and they're 2-pi periodic. So notation for that is this. So the C means continuous. The superscript of 2 means 2 continuous derivatives. The P subscript means periodic. And 0 to 2 pi is the domain. So 2-pi periodic functions. And we use this scalar product, so integral from 0 to 2 pi of f conjugate times g. And the operator we consider is second derivative. So to find its adjoint, I start with the scalar product f and ag, which would be g double prime in this case. And I want to find a way to rewrite this scalar product as the scalar product of some operator applied to F with G. So in other words, I want G by itself and some operator applied to F. So I'm going to carry out integration by parts because scalar product is an integral, and we'll see what we get. So just using definition of A, I have F of G double prime. But using a definition of a scalar product, I have this. Now I apply integration by parts, where F conjugate is the U, and then G double prime is playing a role of the dV. So I get these boundary terms, and then I get this integral. But F and G are periodic, so these functions are equal at 0 and 2 pi. So these boundary terms go away. So all I'm left with is this. But now apply integration by parts to this. So here are my boundary terms. So F prime, F conjugate prime is the U, and then G prime is ds is playing a role in the dV. So I get these boundary terms, and now I have this integral. Because of the periodicity, these boundary terms go away. So now I'm left with this integral. But I want to express this as a scalar product. Actually, I'm going to put an intermediate step here. So this is a scalar product of F double prime with G. But F double prime is the same as AF. So since F scalar product AG is the same as AF scalar product of G, A must be the adjoint of itself. So when you're talking about the space of 2 pi periodic functions, at least, the second derivative operator is self-adjoint or Hermitian.
Have you ever made U equal to the U that you picked?
Oh, basically what I could evaluate, because what do you do with a dV? You take its antiderivative, and so that's why it makes sense to choose dV equal something that already is a derivative to begin with. So yeah, I could have tried to get away to move it down anywhere.
So F conjugate is also periodic, even though you said it's only F and G are periodic?
Yeah, and the way you can see that is if you write F as its real part plus I times its imaginary part, this real imaginary part is periodic.
So G prime isn't necessarily periodic, but because the conjugate is zero.
Well, actually, if you express it as a Fourier series, you find that the derivative with respect to x would not be periodic. I have to emphasize that depends on what Hilbert space you're working with. If I had been using a different Hilbert space, same second derivative operator, I may not necessarily reach the same conclusion that's self-adjoint. Periodic is convenient because it made the boundary terms go away. But for certain other Hilbert spaces, you might not get that. So that's why whether an operator is self-adjoint depends on the scalar product. And so you have to be careful to specify, okay, I'm working with this Hilbert space and this scalar product. Now, we've dealt with basis expansions of functions, like running a function in terms of an orthonormal basis, like we have here. So psi and chi are expressed as expansions in the same basis, orthonormal basis phi n. So suppose chi and psi are related by this equation. So chi is the output that you get from applying the operator A to psi. So what I'd like to be able to do is express the coefficients of the output chi in terms of the coefficients of the input psi. And I can get a handle on that using a scalar product. So what I do is I look at each coefficient of chi. Because the basis is orthonormal, these are the coefficients of chi in the basis of phi k in this case. But now I use the fact that chi is equal to A times psi. And then I use the fact that psi has an expansion in the same basis. So I go ahead and substitute that expansion in. Then I use the linearity of the scalar product. I can pull the summation out. These scalars, Cn, I can also pull them out. And now I'm going to define little a kn to be equal to this scalar product expression here. And the reason why I'm doing that is this right here, you can think of it as a matrix vector product. Now, the matrix vector in this case may be infinite. You know, these really are infinite expansions. But now we see we have a relationship between the coefficients of the input and the coefficients of the output. They're related by a matrix of sorts. And this is how the matrix is defined. So you have, so the entry in row K, column N, comes from scalar product of phi K with A phi N. So if you get a handle on these matrix entries, then you can go directly from one set of coefficients to the other. Questions about the manipulations that happen here? Right. So basically, like I said, it's amounts to matrix vector multiplication. So you can think of it this way: if C is the vector of all coefficients of psi, B is the vector of all coefficients of chi, A is this matrix, then we have this relationship between. And we can also use the matrix to describe the operator A using Dirac notation that we saw before. So here I have chi written in terms of the orthonormal basis, its coefficients. And now I replace Bm with its representation in terms of C's. But now I use a formula for Cn, because these are coefficients in the expansion of psi. So now I rearrange my summations a bit. And keep in mind, psi does not depend on m or n. So I'm allowed to take this ket, if you will, and factor it out to the right. And now we see what's left. Chi was already established to be equal to the operator A times psi. So this expression here in the large parentheses, that is a way of, that is the operator A. So this is how it can be expressed, the operator A can be expressed in terms of these matrix entries. This is similar to what we saw earlier, resolution of the identity. Like if this A and N wasn't here, and you just had a sum over N of graph for phi n and the ket for phi n, that turned out to be identity. Actually, I'll go ahead and fill that in here. Okay, so here we have identity, that's at the end of section 5.1. So this is a special case of this, where little AMN actually defines the identity matrix. Oh, sorry. I in this font is the identity matrix. I in this font is the identity operator. Here's an example. Continuous 2 pi periodic functions. A is a first derivative operator this time. And here's an orthonormal basis for my Hilbert space. So e to the I n x, and the factor of 1 over square root of 2 pi is used to normalize them. In other words, make them orthonormal, not just orthogonal. Same scalar product as before. So what I'd like is the matrix associated with this operator. So that means computing this scalar product. So I fill in what everything is, the operator A and also the basis functions. But then when I take the derivative of e to the I n x, I'll get e to the I n x again times I n by chain rule. And then I can pull out. But these functions are orthogonal. But in fact, if I take the 2 pi in the denominator and write the square root of 2 pi, square root of 2 pi, then I can put those back in here and I actually have my basis functions, phi m and phi n. These are orthonormal. So this is equal to the Kronecker delta, which is equal to 0 if m is not equal to n, and 1 if m equals n. What this means is this matrix, defined by little a m n, is a diagonal matrix. A diagonal matrix has all entries equal to 0 unless the row index equals the column index. So this is equal to in for the n entry. All other entries 0. So in this case, the matrix is particularly convenient when it comes to differentiation and on this Hilbert space of periodic functions. So here's another way. So here's another way how we describe the entries of this matrix. So this actually provides an efficient way to differentiate 2 pi periodic function. You get a hold of its Fourier series coefficients, and you multiply each of them by this factor in for the appropriate n, and then you reconstruct your function from the Fourier series coefficients, then you have a derivative. This is an approach to differentiation that's used, for instance, in what are called spectral methods for solving differential equations. Where getting the Fourier series coefficients and then reconstructing a function of x is carried out using an operation called the fast Fourier transform. So because of its efficiency, it's used quite often. Questions about what was carried out here. The significance of the matrix being diagonal is it makes this summation a whole lot more efficient to evaluate, because the way it is written here for a general operator, I have a double summation for all m and all n. So if A of n finds a full matrix, like all entries non-zero, or most entries non-zero, then evaluating this could be quite impractical. But if the matrix in here is diagonal, then you only have a single summation. Actually, I'm going to go ahead and illustrate that. So our operator is A. That is a sum over M of use N. Oops. N. So this is the way to represent an operator using a single summation rather than a double summation if you get a general case. So if we were able to express an operator A using an orthonormal basis, like I've just done here, how can we express the adjoint in the same way? So here's what I can do. So let's suppose A in this font is the matrix of my operator A. Now I want the matrix B, that's the matrix of the adjoint. So by the definition of a matrix of an operator, I would have this. But this is the same, by the definition of the adjoint, that's the same as if I were to move this operator over to phi m, and now it becomes its adjoint, which is A. So I've used this property here to justify that. But now I can switch the order of operating to my scalar product as long as I take the complex conjugate. And now I have phi n A phi m. Well, this is the nm entry of the matrix represent mn. So, matrix of the adjoint is the adjoint of a matrix, which is also known as a Hermitian transpose. So the Hermitian transpose of a matrix is when you take the transpose and you also take the complex conjugate. I think I mentioned that in the earlier class. That's how you generalize in a complex case, you got to remember to conjugate. So given the matrix of an operator, it's very easy to get the matrix of the adjoint. Just transpose and conjugate. And we see once again how the various properties of adjoints and a scalar product can be used together to show that. Questions about what happened here? Oh, okay. Last thing in the notes. So that's an example of that. So A is first derivative operator. And that turned out, the matrix of this operator turned out to be a diagonal matrix. So to take the adjoint, all you're doing is you're taking a transpose, which keeps the diagonal matrix as a diagonal matrix, but then you got to take a complex conjugate, so this becomes a minus. So what happens is the adjoint turns out to be matrix of the adjoint is minus the original matrix, and from that we conclude that the adjoint of the first derivative operator is minus the derivative. Which actually makes sense when you think about it, because if you recall an example where I worked with a second derivative operator, I performed integration by parts twice. If it was a first derivative operator, I would only use integration by parts once. And other than that, things will work out pretty much the same. But remember, your integration by parts formula is integral of u dv equals uv minus integral of v du. And it's because of that minus in integration by parts formula. But you can also see that the adjoint of first derivative is minus first derivative. That's why it makes sense that if I carry that out twice, the second derivative, I negate twice and back to the original. So the second derivative operator, as shown earlier, is self-adjoint, also known as Summation. First derivative in the space of periodic functions is anti-Hermitian or anti-self-adjoint. And yeah, the easiest way to see that, no integration of parts required, is just taking the adjoint of the matrix, of the original. Now we come to the end of the notes. Questions on any homework problems?
On that one, how would, besides it being bolder on, like, it says that is in nature. Very last one.
Yeah.
No, the beginning of that.
Oh.
The first that is. Besides it being bolder, which tells us that it's a, matrix.
Yeah.
How would we write that, like, for actually reading it?
Oh, okay. Okay, one way you can do it if you're on paper is like, maybe you could adorn it with an accent mark or tilde or something like that as a way to distinguish.
You put a tilde underneath it for my business file.
Oh, interesting, okay,
The note.
that's really weird.
It
But I even assist that.
What better than just making it really bold?
Yeah.
Yeah.
It's more official.
Well, and I think it was in my class, they was talking about how they made a mistake of using lowercase a's and lowercase q's in the same lecture. This is years ago. And the students told me after like 20-something minutes that they could not distinguish my lowercase a's and lowercase q's because I did not make the tail of the q long enough. So now I make it super long. I could change letters, but I just don't want to. Yeah, it's something to the paper, which is why everyone should go late that. Someday. Okay. Because I remember how people used to do math papers before the days of LaTeX, where it's on like an ordinary typewriter, and math symbols hand drawn in. So, and now it's like, oh god, so people. So, okay.
I have a question.
Yeah.
In the homework on problem 1, we're told that we have an orthonormal set of functions. On problem 2, we're told explicitly that our functions are not necessarily orthogonal. But on 3 and 4, we're not told anything. So, or I'm sorry, on 4 and 7, we're not told anything.
Okay, this is unfortunate. For 4, you actually, they kind of slightly work in here, concepts of orthogonality, which means you would need to assume that these functions are at least orthogonal.
Okay.
Yeah. And actually, I think orthogonality would be enough. And yeah,
Number 7, when I go to the place in the text where that inequality was given, in the text, we're told that the phi are orthonormal, but can I assume that here?
Yes, you need to.
Okay.
Yeah, I mean, I was looking at, and answering questions on each one of the problems that we're not always, don't always include all the assumptions they need.
Thank you.
All right. Any other? Okay, I guess we're calling it good.